I am Roland Piabao, ES81 of Section A1, and I am here to present solutions of some first-order differential equations. Are you ready? Okay, let's begin. Our first problem is we need to solve the differential equation y double prime plus y prime squared plus 1 is equal to 0 by separation of variables. We let u is equal to y prime and u prime is equal to y double prime. Now, we substitute u is equal to y prime to the original equation, and that's why we have u prime plus u squared plus 1 is equal to 0. Now, u prime is also equal to du over dx, and that's why we have here du over dx plus u squared plus 1 is equal to 0. Transposing u squared plus 1 from the left side of the equation and transferring it to the right side of the equation, we now get du over dx is equal to negative quantity of u squared plus 1. Separating the variables, we put the u variable to the left side of the equation and the x variable to the right side of the equation, and that's why we have du over u squared plus 1 is equal to negative dx. Integrating the equation, we have the integral of du over u squared plus 1 is equal to the integral of negative dx. Evaluating the integral, we have tangent inverse of u is equal to negative x plus the constant c. Now, u can be written as y prime, so we have here tangent inverse of y prime is equal to negative x plus c. Separating the variables, we have here dy over dx, which is dy prime. It is equal to tangent of c minus x. Integrating this equation, we have the integral of dy, which is equal to the integral of tangent of c minus x dx. Evaluating this equation, we have now our final answer, which is y is equal to negative ln of the absolute value of cosine of c minus x plus k. Now, for our next problem, we have to solve the homogeneous differential equation 3y cubed minus x cubed dx is equal to 3xy squared dy, where y of 1 is equal to 2. We rewrite the original equation into its standard form, and that's why we have 3y cubed minus x cubed dx minus 3xy squared dy is equal to 0. Now we need to check if this equation is a homogeneous differential equation. Now, by inspection of m of x and y, which is equal to 3y cubed minus x cubed, and of the n of x and y, which is negative 3xy squared, it shows that these coefficients are homogeneous functions of degree 3. Now, we let y is equal to ux and dy is equal to u dx plus x du. Substituting y is equal to ux to the rewritten standard form of the equation, we have this 3 times the quantity of ux cubed minus x cubed dx minus 3 times the quantity of ux squared times the quantity of u dx plus x du is equal to 0. Simplifying this equation, we have x cubed times the quantity of 3u cubed dx minus dx minus 3u cubed dx minus 3u cubed x du is equal to 0. Simplifying this equation furthermore, we have negative dx minus 3u cubed x du is equal to 0. Now, separating the variables, putting the x variables in the left side of the equation and the u to the right side of the equation. And that's why we have here negative dx over x is equal to 3u squared du. And integrating the equation, we have the integral of negative dx over x is equal to the integral of 3u squared du. Evaluating this, we have negative ln of the absolute value of x is equal to u cubed plus c. Now, returning the value of u to y over x, we have y over x cubed is equal to c minus ln of the absolute value of x. Simplifying this equation, we have y cubed is equal to x cubed times the quantity of c minus ln of the absolute value of x. Now, at y of 1 is equal to 2, we substitute that if y is equal to 2 and x is equal to 1 to this equation, we have now 2 cubed is equal to 1 cubed times the quantity of c minus ln of the absolute value of 1. And because of this equation, we can acquire the value of our constant, which is now 8. Now substituting 8 to this equation, we now have y cubed minus x cubed times the quantity of 8 minus ln of the absolute value of x, and this is now our final answer. Our next problem is we need to solve the linear differential equation x dy over dx plus 2 times the quantity of 1 minus x squared y is equal to 1. We rewrite the original equation into its standard form, and that's why we have dy over dx plus the quantity of 2 over x minus 2x times y is equal to 1 over x. In solving a linear differential equation, we need to find the integrating factor, which we denote as a v. Now we have v is equal to e to the integral of 2 over x minus 2x, which is this part of this equation, dx. Evaluating the integral, we have v is equal to e to the 2 ln of x minus x squared, and simplifying it furthermore, we have v is equal to x squared times e to the negative x squared. Now, we multiply the integrating factor with the dependent variable, which in our case, we have y as our dependent variable on the left side, and on the right side, we multiply the integrating factor with the f of x. Now, we have the product here of y and our integrating factor. That's why we have d over dx times the quantity of x squared y e to the negative x squared, which is equal to the product of our integrating factor and our f of x. and that's why we have x times e to the negative x squared. Integrating this equation, we have the integral of d times the quantity of x squared times y times e to the negative x squared is equal to the integral of x times e to the negative x squared dx. To solve this part of the equation, we let u is equal to negative x squared and du is equal to negative 2x dx. And that's why we have negative 1/2 du is equal to x dx. Substituting this u is equal to negative x squared to this equation, we have the integral of negative 1/2 e to the u du. Simplifying the integral, we have negative 1/2 e to the u plus c. Simplifying it furthermore, and we return the value of u to x, and that's why we have negative 1/2 e to the negative x squared plus c. Now going back to the original equation, we have now the this result, which is from here, and we have x squared times y times e to the negative x squared, which is now equal to negative 1/2 times e to the negative x squared plus c. Simplifying the equation, we now have our final answer, which is y is equal to negative 1/2 plus c times e to the x squared all over x squared. Our next problem is we need to solve the linear differential equation y squared dx plus 3xy minus 4y cubed dy is equal to 0. Now, we rewrite the equation so that we can acquire its standard form. That's why we have y squared dx is equal to 4y cubed minus 3xy dy. Now we have y squared dx over dy plus 3y times x is equal to 4y cubed. And we have now our standard form, which is now dx over dy plus 3 over y x is equal to 4y. Now, we need to find the integrating factor, which we also denote as v. Now, v is equal to e to the integral of 3 over y dy, which is equal to 3 to the 3, which is equal to e to the 3 minus ln of y, and simplifying it furthermore, we have y cubed. Now, again, we multiply the integrating factor with the dependent variable, which is now x, and equate it to the product of the integrating factor and the f of y. Integrating it, we have the integral of d over dy times x y cubed is equal to the integral of 4y to the 4th. Simplifying this equation, we have our final answer, which is x y cubed is equal to 4/5 y to the 5th plus c. Now for our next problem, we have a mixture problem in a differential equation, and let me read to you the problem. A lake has various streams flowing into it and flowing out of it, the total rates of influx and efflux being equal. For a long time, the streams flowing into the lake are polluted, and pollution in the lake built up to an undesirable level. However, as a result of conservation efforts, the sources of pollution in the streams were eliminated, and now only pure water flows into the lake. If the volume of the lake is V cubic kilometers, and if the rate of influx and efflux is R cubic kilometers per year, and if the pollutants are always uniformly distributed throughout the lake, obtain formulas for the time it will take for the pollution in the lake to be reduced to A, to one-half its level at the time of the cleanup, and to B, to one-tenth its level at the time of cleanup. To solve this problem, we need to use the mixture problem formula, which is dA over dt is equal to input rate of pollutant minus the output rate of pollutant. We need to take note that the input rate of pollutant is zero, since only pure water flows into the lake from the time of cleanup. Now, because the input rate of pollutant is zero, we were left with this equation. dA over dt is equal to negative A over V times the rate of efflux, where A is the amount of pollutant, V is the volume of the lake, R out is the rate of efflux, and T is the time in years. We solved this equation by separating the variables, and we put the A variable to the left side of the equation and the T variable to the right side of the equation, and that's why we have dA over A is equal to negative R out over V dt. Evaluating this equation, we have the integral of dA over A is equal to the integral of negative R out over V dt. Evaluating the integral, we have ln of the absolute value of A, which is equal to negative PR out over V plus the constant C. Now at time is equal to 0, we have the maximum pollutant in the lake, and that's why A is equal to 1. Now, we substitute T is equal to 0 and A is equal to 1 to this equation, and that's why we have ln of 1 is equal to negative 0 times R out over V, which is 0, plus C. From that equation, we have C is equal to 0. Now substituting C is equal to 0 to this equation, and that's why we have ln of A is equal to negative T R out over V. And we have here P of A is equal to negative P ln of A over R out. And that is now our general formula for the time it will take for the pollution in the lake to be reduced. Now the question is, we need to determine the numerical time values for Lake Erie and Lake Ontario given the following data. For Lake Erie, we have volume of 460 cubic kilometers and the rate of efflux, which is 175 cubic kilometers per year. On Lake Ontario, we have 1,600 cubic kilometers of volume and a rate of efflux, which is 209 cubic kilometers per year. We need to find the time it will take when A is equal to 1/2 and A is equal to 1 over 10. Now for Lake Erie, we just substituted A is equals to 1/2 and A is equal to 1 over 10 to our general formula, and that's why we have P of 1/2 is equal to negative 460 times ln of 1/2 all over 175, and we got the result of 1.82. And for when A is 1 over 10, we have here P of 1 over 10 is equal to negative 460 times ln of 1 over 10 all over 175, and we got the value of 6.05. Now we can see that it would take 1.82 years for Lake Erie so that it would only have one half of its original pollutants, while it would take 6.05 years for the Lake Erie to have only its one-tenth of its original pollutants. Now for Lake Ontario, the same with what we did for Lake Erie, we substituted A is equal to 1 half the general formula, and that's why we have P of 1 half is equal to negative 1,600 times ln of 1 half all over 209, and we got the result of 5.31. And we also substituted A is equal to 1 over 10, and that's why we have this equation. T of 1 over 10 is equal to negative 1,600 times ln of 1 over 10 all over 209. And we've got the result of 17.63. And we can see that it would take 5.31 years for Lake Ontario so that it would have only one half of its original pollutants. And it would take 17.63 years for Lake Ontario so that it would only have 1/10 of its original pollutants. Now, we have solved the problem. And that is the end of this video tutorial. And thank you for listening. Once again, I'm Roland Piabao. See you next time. Bye-bye.